Hello everybody. Last lesson we have learned about Coulomb's law, and if we have two charges given here, we know how to calculate the force that attracts or repels these two charges. It was given as K times Q1 times Q2 over R squared. Today's topic will be what happens if we now add a third charge and place it just somewhere. So this is today's topic. The force due to three charges, or more charges of course. If we only had these two charges, we know how to do. We just make an example. Let's let this blue one be charge Q1, and usually blue is negative, but I just use these colors here so we don't confuse them. So I make it plus 20 nanocoulombs, and the red one here is charge here Q2, and it is plus 30 nanocoulombs. So positive, positive, they are repelling, so the blue one will be pushed to the left with a certain force. I call this F2 on 1, and with the same magnitude but opposed, the red one will be pushed to the right, and I call this F1 on 2. If we know the distance, we could also get here the magnitude. Let's assume this is 10 centimeters here in between. Then we can use Coulomb's law, fill in the numbers and get the amount or the magnitude of the force. We will do in this example later on. However, the question is now, what happens if we add a third charge? And I could place this in between or here or here. Just we make a easy example. So I put it 10 centimeters below the one, so that we get here a rectangle basically, and that makes calculations easier. Further down at 10 centimeters again. Let's take this charge to be a negative one, so we call it Q3, and let it be minus 30 nanocoulombs. Then we see here from the magnitude 2030, it was 2030 as well here, 10 centimeters, 10 centimeters. So the forces will be equal in magnitude, but here minus and plus, it will be an attractive force. So the blue one will be pulled down by this green charge, and we call that F3 on 1. And it is the same magnitude as the red one, so I make the arrow with the same length as here. And the green one will be pulled up by the blue, and this is then same force, so I make it the same length for this force, F here 1 on 3. The question just is that true? So we have said if we have these two, then that's the force in between. And now I have said if we have these two, this is the force in between. But the question is, isn't maybe this charge affecting the original forces that we had up there? Fortunately, it is not. So we can just follow like that and just say, what are these two doing to each other? Then these two, and a last step, the two other ones here. The spacing in between here will be larger, and the force will be then that the green one, it's plus and minus, so it is attracting. So the green one will be pulled up in this direction. So this is then F of charge 2 acting on 3, and the red one will be pulled to this direction, same length as this vector here, which is F3 on 2. We have now just calculated for each individual pairs of charges what the force is, and we can now get the net force on each one by adding these forces as vectors. I can draw this. I have completed here these shapes, and the resultant is then the diagonal. We get here 3 final resulting net forces acting on charge 1, on charge 2, and on charge 3. Let's just write down this principle of superposition, as it is called. When a number of charges are interacting, the electric force between two charges is not affected by the existence of the other charges, and the total force on a charge is the vector sum of all the forces due to other charges. So let's start with calculating the resultant force on charge 1. I have copied the situation down here, and first of all we have to go back and look at what is F21. F21 is the force in between these two, so we have to take Q1 20 and Q2 30 nanocoulombs, and R is 10 centimeters. So let's put that in. F21 magnitude is given as K, which is 8.99 times 10 to the power of 9 Newton meter squared per Coulomb squared. Then the two charges and R squared. This amounts to 5.4 times 10 to the power of minus 4 Newton. If we go back, then we see that the magnitude of these two compared to these two charges is the same, so it's 30 and 30. Also the distance is the same, therefore also the magnitude of the green force is equal. What is then the resultant force? when we have here two vectors that are equal and we have here then therefore a square, then we know the length of the diagonal is square root of 2 longer than a side. So the resultant force 1 is square root of 2 times 5.4 times 10 to the power of minus 4 Newton, which is 7.6 times 10 to the power of minus 4 Newton. Now let's see what is the force on charge 2. Again, I have copied the situation, and we of course already know the force F12 because it's the same as F21 and for example F13 as we had, but what we have to calculate is F32. Let's go back to the drawing and see the situation. So the charges are 30 and 30 nanocoulombs, and we have now a new r, a distance in between. How much is that? It is simply square root of 2 times longer. Again, this one is a square, so we can use the Pythagorean theorem. 10 squared plus 10 squared, square root out of it is the same as square root of 2 times 10 centimeter, which amounts to 14.14 centimeters. Now we have all the data to put it into Coulomb's law. Now we have to look at the angles. Let's go to the original drawing again. We can see here that this triangle, 90 degree here, and this angle has to be the same. Therefore, the angle up here has to be a 45 degree angle. This green one has the same incline as that one. Therefore, this angle as well is a 45 degree angle. So let's transfer that to our sketch. So what we know is the blue force, then the green force, which of course I can also draw here, and we want the white one. The easiest way is if we use the law of cosine. We just take this resultant force here to be C, and then A is that one, the blue force, B is the green force, and the angle is 45 degree. So let's calculate C. I have put in all the numbers. To make it easier, I just have taken the 10 to the power of minus 4 Newton out of it. So I just get here 5.4 squared, 405 squared, 2 times A times B times cosine of the angle in between, and the calculator just gives you the result of 3.8 times 10 to the power of minus 4 Newton. The same idea can be applied now to calculate the third net force. I leave this up to you as an exercise. I have gotten the result of 8.7 times 10 to the minus 4 Newton.